before we're able to use the technology to be able to do some sketches, what I like being able to do is to be able to sketch things by hand. And of course, I'm going to have to add in a little bit extra information to actually tie into what we're going to have to do. So some recall from what we had done last year in Foundations 20. One thing is that a number is a zero polynomial if you basically plug a number in and it gets equal to 0. So we'll talk about that in a second. Other words that can be used for 0 are root, solution, answer, X-intercept. So for example, 2 is a 0 of the function x minus 2 squared. So because if you plug 2 into here, well, 2 subtract 2 is 0, 0 squared is 0. So that's going to be a 0, which means it's a root, solution, it's an answer, it's an x-intercept. One other thing that kind of ties back to grade 9 is what's known as tangent to. Tangent line or tangent point is where a line or curve just touches at a certain point. In grade 9, we talked about it as circles, and a tangent point being something that just touches a graph. So that would be the point of tangency. So we're going to talk about some how zeros talk about. We'll talk about, and then we'll get into some graphing and some understanding. So if a number is a real zero, multiplicity 1, the graph of the polynomial will simply cross the x-axis at that point. But it will not be tangent to. So what that means is we just have to find out the zeros of our factors. So x minus 2, well, x minus 2 equals 0 at x equals 2. What that means is at 2, our graph will simply cross the x-axis, but it will not be tangent to. Now, of course, this one works out really nicely because it's also the equation of the line, x subtract 2, and our line would look like that. If our factor, or if our 0 is a real 0 of even multiplicity, basically talk about how many times it occurs, the graph of the polynomial function will be tangent to the x-axis, but it will not cross the x-axis at that point. So we know that x minus 2 equals 0 at x equals 2. So what that means is at 2, because it has an even multiplicity, in other words, it's talking about how many times it occurs. X minus 2 squared is x minus 2 multiplied by x minus 2. Because it occurs twice, what is going to happen is the graph actually, I know that the graph is not perfect, it's going to go, basically, just touches the line, touches the x-axis, and then just goes back. And if we have an odd multiplicity greater than 1, say 3, because x minus 2 cubed means x minus 2 multiplied by x minus 2 multiplied by x minus 2. The graph of the polynomial function will be tangent to the x-axis and cross the x-axis at that 0. So again, we know x minus 2 equals 0 at x equals 2. So at 2, what is going to happen is our graph is going to come up to that x-axis. It's going to go tangent to it and is going to cross, which makes it look much more like a cubic. A squared makes your graph look like a squared. To the power of 1 makes it look like a line. To the power of 3 means it's going to look like a cubic. And that's what that characteristic is from the first section. So let's talk about what that really means in all context. So our first example, we're going to use this following polynomial function to answer the following questions. Now I know that this specific example is actually above Foundations 30, but we're using it to help understand what the characteristics are. So if we want to determine the zeros, we have to look at our factors. So tying back to Foundations 20, our factors, we set them equal to 0. So we have to say x minus 2 equals 0. Well, where does x minus 2 equal 0? We add the 2 to both sides. X would equal 2. X minus 4 is another factor. Well, where does x minus 4 equal 0? We would add the 4, and x would equal 4. X plus 3 equals 0. We have to subtract 3. So x would equal negative 3. The degree of this function is why this is not specifically Foundations 30. Again, we're talking about characteristics. We want to be able to graph, because if you're taking this course, more than likely you are going to be going into something university where you're going to have to know a little bit more about this. So the degree of the function is literally just adding up our exponents. So this is an exponent of 2. This is actually an exponent of 1. And this is also an exponent of 1. So if we took 2 add 1, the degree of this function is 4. The leading coefficient, well, all of our first terms are all positive, which means our leading coefficient is positive, and that's all that we really care about. At the same time, we don't even really need to necessarily care what the degree is. What we do need to care about is that 4 is an even number. So if we do have an even degree and our leading coefficient is positive, that means that we're going to have to start in quadrant 2 and end in quadrant 1. So we have its end behavior. So we found all of our zeros, and now we're going to talk about their multiplicities and how they're going to behave at 0. So we have a 0 of 2. So its multiplicity, in other words, it's asking how many times it occurs. So this multiplicity talks about how many times it occurs. An x minus 2 occurs 2 times. And if it occurs 2 times, it means it's going to be tangent to, but will not cross. The 0 of x equals 4 only has a multiplicity of 1. It only occurs once in here, which means multiplicity of 1, it's just going to cross. It will not be tangent to the x-axis. So it's just going to cross. Our last 0 is negative 3. It also has multiplicity of 1, which means it is just going to cross. So what does that all mean? Well, we're going to have to tie everything together. We have an even multiplicity, leading coefficient is positive, which means it starts in quadrant 2 and ends in quadrant 1. When I start learning how to sketch, I start off saying, well, I'm going to have to start up in quadrant 2 and I'm going to end in quadrant 1. Then I'm going to label my zeros. I'm going to put my zeros on my x-axis. I have a 0 of 2, I have a 0 of 4, and a 0 of negative 3. Again, the other word for 0 is x-intercept, or root, solution, answer. All right, now the last thing that we're going to do is we're going to look at these characteristics, look at our end behavior, and use our x-intercepts. So at the x-intercept, and the one last thing is as we're sketching, we always want to go from left to right. So we're going to have to start up in quadrant 2. It doesn't really matter where you start. You can start here, you can start here. As long as you start in quadrant 2, you're all good. So when our graph gets to negative 3, it's just going to cross. I'm just going to move that over a little bit. make it look like it's actually crossing right at -3. So we're going to cross. Now, the next part, if we actually have everything in standard form, we could identify what our y-intercept is really nicely. This one specifically, our y-intercept is actually going to be -48. For the sketching, now at Foundation 30 level, I wouldn't necessarily expect you to have that known, at least not now. I may incorporate it a little bit later on. But if you know what your y-intercept might be, if it's for sure off the grid, I just say go off the grid. Now I know I'm going to have to come up again because at this x-intercept of 2, it is going to have to go tangent, but it's not going to cross. What does that mean? If it's going to go tangent to and not cross, because of it, it has a multiplicity of 2. A multiplicity of 2 kind of means degree 2. Not specifically, but to help have an understanding of it, it does work. Which means at that 0, it's going to behave like a parabola, which means it's going to touch it and go right back down, which makes this a parabola. Now the last thing that we need to do is at our 0 of 4, it's just going to cross. So cross the x-axis at 4. And what we have just now done is we have started up in quadrant 2 and ended up in quadrant 1, just like we are supposed to with an even positive polynomial. Another way that you could potentially sketch this, I wouldn't necessarily encourage it just because I know that, actually no, I'm not even going to show that. This is probably the best way. Some graphing technology that you could download on your phone or even on computer, Desmos is a good free application that allows you to do good sketching. All right, next example. We are going to sketch the graph of a 5th degree polynomial whose leading coefficient is positive, has one negative real root of multiplicity 2, and a positive real root of multiplicity 3. Okay, so again, I know that 5th degrees are not in the Foundations 30. It's looking at the characteristics. I just want to be able to identify different parts. So we have a negative root that has multiplicity 2 and a positive root of multiplicity 3. We also know that it's a 5th degree, which means it's odd, but its leading coefficient is positive. If it's odd and the leading coefficient is positive, it means that's going to be going from quadrant 3 to quadrant 1. So it's going to have to start in quadrant 3 and it's going to end in quadrant 1. By using our roots, we'll also be able to do proper sketching. Now, if it just says that we have a negative real root, it could be anywhere. I'll just put it right there. So if I start off by starting in quadrant 3, multiplicity 2 means I'm going to go up to that x-axis, go tangent to, and not cross it. I'm going to come right back down. This has provided me with the opportunity to be multiplicity 2 because I've just gone tangent to and not crossed the x-axis. But having a positive real root, sorry, I'm just going to label that as a nice green point. Having a positive real root of multiplicity 3, again, can be anywhere. I'll put it right there. I'm going to continue on with my graph. Multiplicity of 3 means I'm going to have to come up, go tangent to the x-axis, and cross. I have now just ended in quadrant 1. Just add my arrows on. This is a possible sketch. It's not the only sketch. I can make everything really nice and shallow. My graph could look like that. There are multiple answers to something like this. These are just 2. Alrighty. This one, let's talk about more things. So for each of these graphs, we're going to talk about the least possible degree, sign of the leading coefficient, what the x-intercepts are, and the factors of the function with the least possible degree. So really what I want to do is I want to find out essentially what is the possible equation of this. So the least possible degree talks about, okay, so let's label this I, and I. So the least possible degree talks about, well, how many possible x-intercepts are there? Well, in this one, there are exactly 3. In this one, it's a little bit harder to tell. For the only reason that this one actually shows all of those x-intercepts clearly defined. The degree overall talks about the maximum amount of x-intercepts. No matter where I move this graph, either up or down, the maximum amount of x-intercepts is 3. There's 3. There's 1. There's technically, yeah, there's 1. But the maximum amount is 3. If I talk about this one, yes, I can see that there's only 3 x-intercepts. But if I take my graph and I do some special things to it, I can see what its maximum degree would be, or what its possible degree is. If I move this graph down, you'll see that I only have 1, 2 x-intercepts. If I move it even further down, there's only 1 x-intercept. But as I keep on moving up, if I were to have it moved up to here, I could read it as 1, 2, 3, 4 x-intercepts, which means that that is actually its least possible degree. Again, degree 3 is not Foundation 30 curriculum. Sorry, higher than degree 3 was to help understand characteristics. The sign of the leading coefficient? Well, the easiest way is finding out where does it end. This graph ends up, which means it's going to have to be positive. This graph, though, ends down. Because it ends down, it would have to be negative. We can actually read specifically what our x-intercepts are because they're actually labeled. Our x-intercept here is -4. This one is -2. This one's +2. This one is -5. This one's -1. And this one's +4. Which means we actually have some factors. So because our x-intercepts are -4, -2, and 2, its factors would have to be x add 4, x add 2, and x subtract 2. Because these zeros are the zeros of each of these factors. If I plug -4 into here, this makes this 0. If I plug -2 into here, this is 0. If I plug 2 into here, it's 0. My x-intercepts here are -5, -1, and 4. Its factors would then be x add 5, x add 1, and x subtract 4. Now it's not on there right now, but I think I should probably add it in, is what is the equation? What's happening right here? What kind of graphing is happening at this -4? Well, it's just crossing. If it's just crossing, that means that this x plus 4 has a multiplicity of 1. So I wouldn't necessarily have to write the 1. This x subtract 2, or sorry, x equals -2. So the factor of x plus 2. This one, the graph is also just crossing, which means the x plus 2 has a multiplicity of 1. And this one also, has a multiplicity of 1. Last thing I need to make sure is that my equation is positive. Well, we have positive x that would actually be multiplied by positive x, which we multiply by positive x. Yep, it's going to be positive. We're all good. This equation, the x add 5, which has an x-intercept of -5, this is just crossing, which means x add 5 would have multiplicity of 1. This -1, 0, which means a factor of x plus 1, also has a multiplicity of 1. This 0 of x equals 4, which has a factor of x minus 4, it's behaving differently than the other ones. The graph goes tangent to, but it does not cross, which means it has a multiplicity of 2. Now, if we were to take an x and multiply by an x and multiply by an x, even an x squared, it would still be positive. The last thing we're going to need in this equation, I just need to move this slightly over. Last thing I would need in this equation is a negative in front. And now I have a negative, and this would be a quartic graph. But you only would have to memorize, you would only have to know constants, linears, quadratics, and cubics. It doesn't hurt to be able to know how to graph. And our last page. Our last equation, or sorry, example, is the equation d equals 0.008 s squared adding 0.539 s subtracting 10.449 is the equation which models the speed of a car, s, in kilometers per hour, and the distance, d, in meters needed for it to stop. Now, obviously, this would be ideal situation, ideal friction, ideal constants, basically ideal stopping conditions. What is the distance needed for a vehicle to stop with the vehicle going 30 kilometers per hour? Well, that's pretty easy. What would be the distance? So we're solving for distance. We have speed, which means wherever we see speed, we're going to have to plug in 30. So 0.008, 30 squared, adding 0.539 multiplied by 30, subtracting 10.449. Simply by plugging that into my calculator, I get 12.921 meters. So if you're going 30 kilometers per hour, you slam on the brakes, it would be almost 13 meters for you to stop. What about if the vehicle was going 50 kilometers per hour? Well, it just means that we're going to be plugging 50 in. And we plug 50 in for each of the S's. And if we do that, we get 36.501 meters. So how does this overall talk about our equations? How does it talk about our polynomial functions? Well, if we were to graph this, because it's a square, it would be turning into a parabola. So our parabola would look like something like this. Of course, this would be a very rough sketch. Speed would be on the x-axis, distance would be on the y-axis. So why do we have to have an understanding of what this really means? Well, that's actually exactly what this question is asking. How do these numbers compare? Well, if you're going 30 kilometers per hour, it takes you 13 meters to stop. Approximately. But you increase your speed by only 20. You haven't even doubled your kilometers. You haven't even doubled your speed. You have almost tripled your stopping time. This is not even doubled. And this is almost tripled. For this exact reason is the reason that small towns, our speed limit in school zones is 30 kilometers per hour. 13 meters to stop. And again, that's ideal situations. Most of our school year, though, is in winter driving conditions. Because of coefficients of kinetic friction and static friction, this 13 meters increases drastically with ice. A lot of Saskatchewan has also changed their speed limits in school zones to be 30 kilometers per hour. It used to be 40. If we were to change this number to be 40, what does that change? It's about 24 meters. It's 23.911. So it has almost doubled this by just adding 10 kilometers. By adding 10 kilometers per hour onto this, it has almost doubled the stopping distance. So you have someone rush out, an elementary kid rush out from their school, 30 kilometers per hour, a lot less likelihood of you crashing into them and injuring them. 40 kilometers per hour, well, that's a long stopping distance. 50 kilometers per hour, it's not even going to happen. So the understanding of what these formulas mean and how it plays into effect on so many different things absolutely is an essential part of math. Alrighty, sorry for the heavy. That should be good, and you can have some fun. There's a question. I know if there's a question in the textbook that I say you have, as well as an extra handout, obviously. You can have some fun.